Hello guys, how are you? As you can see, it is still raining outside and I'm starting to get depressed. So I think I have two choices. So either I will kill myself or I will make another video on the integer part function. And after some thinking, I think I would choose the latter. So, in this video, we will try to prove that the integer part of x plus the integer part of minus x is equal to 0 if x is an integer and is equal to minus 1 if x is not an integer. Alright, so as we can see we have two cases. The first one is when x is an integer and the second one when x is not an integer. So we will try first the case where x is an integer. So case 1. So if x is an integer, then the integer part of x is x itself. And since x is an integer, then minus x is also an integer, and the integer part of minus x is still minus x. But then, by adding those two up, so we get the sum of the integer part of x plus the sum of the integer part of minus x is equal to x plus minus x, which is x minus x, which is 0. So case 1 is proved. Now when it comes to case 2, that is when x is not an integer, I'm going to do two different solutions. The first one goes after the definition, the exact definition of the integer part, and the second one is a bit more sophisticated. So let's start with the first solution. So now if x is not an integer, this means that according to the definition I have this double inequality, but notice here that the sign equality is gone here, and this is not a surprise because the equality here holds whenever x is an integer, but this is not the case. So the equality sign here vanishes because x is not an integer. Okay, so, and by multiplying now this double inequality by minus 1, so this one, by multiplying this double inequality by minus 1, it will be flipped and we get this new inequality. So minus integer part of x minus 1, strictly less than minus x, strictly less than minus integer part of x. But this is, according to the definition, the exact definition of the integer part of minus x, because take a look at here, minus integer part of x minus 1 is the greatest integer less than or equal to minus x. So according to the definition, the integer part of minus x would be exactly minus the integer part of x minus 1. And by moving this term to the left hand side, so we get what we want. So this was solution 1. Now solution 2, which is more sophisticated. In this solution I'm going to need one fact from an earlier video which said that the integer part of x plus n is equal to the integer part of x plus n, where x is a real number and n is an integer. And the second fact I will use is that if f of x plus t is equal to f of x for all x where t is a real number greater than 0, then f of x is periodic with period t. So I'm going to use these two facts to make another solution now. Alright, so to begin with, I will let f of x be a new function defined as follows, as the integer part of x plus the integer part of minus x plus 1. And what I'm gonna do here is I'm gonna prove that f of x is 0 for all x that are not integers. So I will show here that f of x is equal to 0 for all x that are not integers. And to do this, I will first try to find out what f of x plus 1 gives. So now by changing x to x plus 1, so I get, so the integer part of x plus 1 plus the integer part of minus x minus 1 plus 1. And now I'm going to use this first fact, which says that if I have an integer inside the square brackets, I can move it out and still have this equality. And this is what I'm going to apply here. So instead of x plus 1 here, I will take the integer part of x plus 1, and the same here, it will be the integer part of minus x, and minus 1 will be moved outside the brackets, plus 1. And notice now that 1 and minus 1, they cancel out each other, and we have left the integer part of x plus the integer part of minus x plus 1, which is in fact the function f of x. So what have we done here? So we have shown that f of x plus 1 is equal to of f of x, but this means that f of x is periodic with period 1, which in its turn means that it is enough for me to study f of x on an interval of length 1. So because the function is periodic with period 1, it is enough to study f of x on an interval of length 1. And this is what I'm gonna do. So if I choose the interval, the open interval 0, 1, so if x is in this interval, then minus x will be in the open interval minus 1, 0. So I will flip this one and multiply with minus. So now, if x belongs to the open interval 0, 1, then the integer part of x is 0. And if minus x belongs to the open interval minus 1, 0, then the integer part of minus x is minus 1. And which means that f of x would be x, the integer part of x, which is 0, plus the integer part of minus x, which is minus 1, and then plus 1, which gives me 0. Thus, we have now shown that f of x is 0 whenever x is in this open interval 0, 1. But we know that f of x is periodic with period 1, which means that f of x is equal to 0 on each open interval of length 1, which means that f of x is 0 on the union of all such intervals of length 1 with n belongs to the set of integers, which finally means that f of x is null whenever x is not an integer. So r minus z means that x is not an integer. So finally, f of x, which is this sum, is 0 whenever x is not an integer, and consequently we have shown that the integer part of x plus the integer part of minus x is minus 1 for all x, not belonging to Z. And to go back here, so we have shown this nice inequality. Now thanks for watching, and see you in the next video. Bye bye.